All right, hello everyone. Welcome back to Physics 40C. Today we're going to be taking another look at Gauss's law and Gaussian surfaces in general and how they tie back to electric charge. So just to do a little bit of review, I'm going to go ahead and rewrite Gauss's law. So we have flux equaling the derivative of the E field times the derivative of area. And so we learned in this last Tuesday's lecture that this can sometimes and very often is rewritten as E times A perpendicular. And it should be mentioned that this perpendicular area is also known as a surface. And so where Gaussian surfaces start coming in is we want to take a look at the flux, which is this term here, caused by an E field going through a particular area. So sometimes we won't always have a free area just kind of floating around. So what physicists have done is created theoretical areas. So Gaussian surfaces are just theoretical areas. So it's not necessarily there is a cube around this infinite plane of charge. It's just that if you were to take the shape of a cube, you could potentially find something out about either the E field or the flux. So Gaussian surfaces most commonly are cubes, spheres, or cylinders. And so they're most often referred to these things because they all have some degree of symmetry. So with cubes, there are many ways that you could cut them and still have two equal halves when you were done. The same with spheres and cylinders. And so why that becomes important is we start looking at what are called net charges. So for net charges, we have another version of this E. So E net is equal to the only difference between this net formula and the regular flux formula is this circle figure right here. And all the circle means is that we're taking the sum of all of these values over an entire surface. So previously in the last lecture, we were doing mostly flows through two-dimensional surfaces. So potentially a flow through something like a hula hoop or more of a flat disc or hoop related shape. Now we're kind of moving into the three-dimensional space. And so that's why we need to take the sum of all surfaces. So sum of all surfaces. So this can also be rewritten as the sum of the fluxes. So we have the flux from the top plus the flux from the bottom and the flux from the sides. And all of these values are relative to these shapes. So a cube, if you're just looking at it, you can usually say, oh yeah, it has a top, bottom, and sides. But in reality, it's just any configuration in the space. So it could be, a cylinder kind of at an angle like this, or, a more diamond-shaped or a cube tilted on one of its vertexes. It really doesn't matter about the shape in particular, just to know that there's a top, a bottom, and the sides. So once you know what direction that the E field is coming from, in the top, bottom, and sides, you're allowed to start knowing something. You're allowed to know a certain quality about the E field itself. So if the net flux into whatever your Gaussian surface is negative, remember that will usually look like E fields being attracted to the object. So if you've got a negative charge in there, you'll have your E field lines going towards it. That will usually that always translates to a QNet, a negative QNet charge. So negative flux net, meaning the E fields are going towards the Gaussian surface, will mean a negative net charge inside. And then the same is also true for positive. So you'll have E fields radiating out from it. So almost as if it were just another point charge, you would also have positive there. And then also, lastly, if you have zero E field, so nothing's really coming in or out, you can usually assume that the Q net is 0 as well. Now that doesn't mean that there are no charges in there at all. It just means that the sum of the charges, where we get this net term from, is 0. So there could be positive charges in this negative net flux, but it just means that there are more negatives than positives. So once we kind of understand those properties about flux, we can make the relationship back to charged particles and what we were doing a few lessons ago. So we know that, well, hold on. We know that the flux, the net flux of an object, of a Gaussian surface, is this E times dA. But what was also introduced to us is this concept that this is also then equal to Qn over the permittivity constant. So this permittivity constant, just a reminder, is equal to 8.85 times 10 to the negative 12 coulombs squared per meter squared times newtons. So this really brings our relationship and our knowledge of these different terms all together, because it's relating the E fields with the charged particle inside and the permittivity constant as well. And so it should be noted that this Qn is the charged, or really the net charge inside the Gaussian surface. So if we know the flux, this term here, we are very, very close to knowing Qn, since the permittivity constant is known. This is what's considered as a universal constant. Then we're only a short ways away from knowing the strength of the E field, since we know the area. And then just another quick reminder of what E field itself is equal to. So we have E is equal to 1 over 4 pi permittivity constant times Q over R squared. And so these equations kind of lay down the basic framework of some of the problems that we're going to be having in lecture and in the homeworks. And if you need any more help with this or just want some more practice, please feel free to come to office hours, both for the professor or the TA or myself at the SI sessions. We'll be going over a lot more in detail about how to use these and what situations they come up. So thank you guys so much for tuning in. See you next time.